Welcome to Machine Learning and Geoscience, a course that will pave your way into the world of data-driven discoveries in the earth sciences.
In this course, we are set to tackle real-world business problems using machine learning within the geoscience domain. We'll follow a structured workflow that begins with gathering data, which is the foundation of any data-driven project. The gathered data may consist of various well logs, rock samples, or any other relevant geoscientific measurements. Once we have our data, the next step is to prepare it. This involves cleaning the data, handling missing values, and ensuring that it's in a format suitable for analysis. After preparation, we analyze the data to understand patterns and relationships that could be predictive. With our data ready and understood, we move on to the core of machine learning, training and testing models. Course 501, Machine Learning in Geoscience. Chapter 2, Visualize and Explore Data. Welcome to the second chapter of Machine Learning in Geoscience, where we dive into the crucial techniques of data visualization and exploratory data analysis. The log plots function is a robust tool for visualizing complex well log data, essential for detailed geoscience analysis and decision-making processes. Its comprehensive approach and customizable features make it a valuable asset for any geoscience data analysis workflow. Let's return to our notebook and see how to apply the log plots function to visualize well log data. Below is the code that demonstrates how to select a specific well from our dataset and then use the function to create a detailed plot of its log data. Chapter 6 of Machine Learning in Geoscience addresses various aspects of logistic regression and classification evaluation metrics. In the current plot, the probabilities for the lithologies lime and halite are shown using logistic regression based on the ROB feature. The probability curve for lime is drawn in green, while halite is represented in blue. Here's how to interpret the plot. The plot represents the logistic regression model's estimation of the probabilities of a sample being either lime or halite, given the ROB feature. The x-axis shows the ROB values, ranging from about 1.6 to 3.0. The y-axis shows the probabilities ranging from 0 to 1. The green curve represents the probability of a sample being lime, while the blue curve shows the probability of it being halite. The decision boundary, indicated by the vertical dotted line, represents the ROB value where the model is 50% confident in either class. This point is around a value of 2.2. The arrows depict the classification decision. Values to the right of the decision boundary are classified as lime, while those to the left are classified as halite. The data points on the plot show actual samples. Blue squares represent halite samples, and green triangles represent lime samples. The provided code snippet outlines the creation, training, and prediction steps for a logistic regression model using the logistic regression class from scikit-learn. Here's a breakdown of each component of the code. Logistic regression model setup. Python log CLF equals logistic regression c equals 0.1, max iter equals 100, solver at liblinear. Logistic regression is the logistic regression model from scikit-learn. C equals 0.1. This is the inverse of the regularization strength, C. Lower values specify stronger regularization, which helps to reduce overfitting but can increase underfitting. Max iter equals 100, the maximum number of iterations taken for the solvers to converge. Solver equals liblinear, specifies the algorithm to use for optimization. Liblinear is a good choice for small datasets and binary classification. Model training, Python log CLF fit xtrain ytrain. This line trains the logistic regression model using the training dataset xtrain and ytrain. The model learns to map the feature vectors in xtrain to the target vector ytrain. Prediction, Python ypredlog equals log CLF.predict xtest. Once the model is trained, it is used to predict the target values for the test dataset xtest. 10-4, parallel processing. 10.4.1, speed and efficiency. Intention, this section demonstrates the benefits of using parallel processing with XGBoost, highlighting how it can significantly speed up model training, especially when dealing with large geological datasets. The comparison between CPU and GPU processing times is essential for understanding the efficiency gains achievable with GPU acceleration. This is particularly relevant for geoscientists who often handle large and complex datasets. Explanation and detailed code walkthrough. Lists CPU times and GPU times to store computation times, and data percents to store the percentage of data used in each step. CPU times, GPU times equals data percents equals. 2. Loop to calculate computation time for different data sizes. A loop runs from 10% to 100% of the data, increasing by 10% increments. This allows for observing how computation times change with varying data sizes. Python for I in range 111, data percent equals I10, data percents.append data percent. In this section, the benefits of parallel processing in XGBoost are demonstrated by comparing CPU and GPU computation times for different data sizes. The code showcases how to set up and train XGBoost models on both CPU and GPU, highlighting the significant speed improvements achievable with GPU acceleration. This efficiency is crucial for handling large geological datasets, making the model training process faster and more manageable. The plot demonstrates the computation times for training an XGBoost model using both CPU and GPU as the dataset size increases from 10% to 100% in increments of 10%. Here's an interpretation of the plot. Computation time analysis. CPU computation time, blue line. The blue line shows the computation time for the CPU. As the percentage of data used for training increases, the computation time increases significantly. The increase in computation time appears to be almost exponential, indicating that the CPU struggles with larger dataset sizes. GPU computation time, orange line. The orange line shows the computation time for the GPU. The computation time for the GPU increases at a much slower rate compared to the CPU. The GPU maintains relatively consistent performance, even as the dataset size increases, indicating better scalability. Interpretation of the well log plot. The provided well log plot displays various tracks that represent different well log measurements and lithology predictions. Here's a detailed interpretation of each track and a comparison of the model output results. Tracks explanation. 1. Depth track. Track 0 shows the measured depth, MD, in meters. Depth intervals are marked along the y-axis. 2. Formation tops. Track 1 displays formation tops as horizontal lines. Labels indicate the names of formations at respective depths. 3. Caliper bit size. Track 2. Red line represents caliper, Cali measurements. Blue line represents bit size, BS, measurements. Shaded areas indicate the difference between bit size and caliper. 4. Gamma ray SP. Track 3. Green line represents gamma ray GR measurements. Pink line represents spontaneous potential SP measurements. Shaded areas indicate the gamma ray values. 5. Neutron density, track 5. Red line represents bulk density, RO, measurements. Blue line represents neutron porosity, NPHI, measurements. Shaded areas show the comparison between RAB and NPHI. 6. Decision tree pred, track 8. Displays lithology predictions made by the decision tree model. Colors represent different lithologies according to the legend. 7. Logistic reg pred, track 9. Displays lithology predictions made by the logistic regression model. Colors represent different lithologies according to the legend. 8. Random forest pred. Displays lithology predictions made by the random forest model. Colors represent different lithologies according to the legend. 9. XGBoost pred, track 11. Displays lithology predictions made by the XGBoost model. Colors represent different lithologies according to the legend. 10. Lithology, track 12. Displays actual lithology labels. Colors represent different lithologies according to the legend. 11. Legend, track 13, displays the color codes for different lithologies. Model output comparison. Decision tree pred. The decision tree model shows a fair amount of detail and differentiation in lithology predictions. However, there are instances of noise and incorrect predictions, especially in minority classes. Logistic reg pred. The logistic regression model also shows a detailed lithology prediction. It seems to handle transitions between formations better, but may not capture minority lithologies as effectively. Random forest pred. The random forest model shows smoother transitions and less noise compared to the decision tree model. It provides a more balanced prediction across different lithologies, but still struggles with minority classes. XGBoost pred. The XGBoost model shows the best performance among the four models. It captures the majority of lithology classes accurately and shows fewer misclassifications. There is a clear improvement in the prediction of minority classes. Best candidate selection, accuracy and performance. XGBoost has shown higher accuracy and better handling of imbalanced classes due to its advanced algorithms and handling techniques. It provides a more reliable and robust prediction of lithologies compared to other models. Interpretability. XGBoost's predictions align more closely with the actual lithologies. It reduces noise and misclassifications, making it easier to interpret the results. Conclusion: XGBoost is selected as the best candidate for predicting lithologies from well-logged data. It balances accuracy, interpretability, and robustness, making it the most suitable model for this task. Final remarks. The comparison demonstrates the superiority of the XGBoost model in handling well-logged data and predicting lithologies accurately. Its ability to handle class imbalance and provide detailed predictions makes it an excellent choice for geological applications.